Shear design for concrete beams ensures that they don't crack under diagonal cracking. There are 3 steps to shear design. First, we work out applied shear force. Secondly, we check that if the beam is sufficient to resist this shear force. If it is not, then we provide stirrups. Now, what are stirrups? Stirrups are metal loops that are wrapped around the beam. Using stirrups or metal loops ensures that the beam is safe from cracking, at least shear cracking. In this lecture, I will explain the theoretical background to shear design of reinforced concrete beams as per Eurocode 2. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore civil engineering and human skills to help us lead more productive, happy, and examine life. So my today's lecture is in continuation of reinforced concrete design. Firstly, we said singly reinforced concrete beams and we designed tension reinforcement or bottom bars. And then we went ahead and designed doubly reinforced concrete beams. And now today's lecture is about shear design for reinforced concrete beams. And shear design is something which you see these links or stirrups. These are termed as shear design. Now shear design in Eurocode 2, it is a little bit more complicated than previous British codes. So bear with me, you will see a lot of formula. But we will do one example as well to make you understand what is it about. But these formula, I mean, they look a bit difficult, but they are not actually. You just have to follow a recipe. But I've tried to collect the information in as concise way as possible. Shear is a major issue in reinforced concrete beams, and we always want to ensure that the failure is in bending rather than shear. The reason is that shear failure is sudden. It is a brittle failure, and at all costs it should be avoided. And the way we design for shear is to provide these rings. The rings that you see wrapped around these top and bottom longitudinal reinforcements, these are termed as stirrups or links. And at the bottom, these bars, these 3 bars, these are tension reinforcement or main reinforcement. At the top, you can see compression reinforcement, or sometimes we call them as hanger bars if they are not required. And then again, you can see you have concrete cover to this beam. And our main purpose today is to design these stirrups or shear links. We already designed these tensile reinforcement and the compressive reinforcement. Now, how do we design shear reinforcement? This is the section of a beam and the vertical links. These are shear reinforcement. Now you can see that the spacing for shear links or stirrups, it is closer at the ends, and in the center you can see that the spacing is little bit larger. I mean, typically you can have like 200 millimeter spacing or something, and in the center 300 millimeter. What is the reason for this closer spacing at the supports and larger spacing at the center?
Because of maximum bending moment at the supports, it will causes the shear cracks on the supports.
Does maximum bending moment happen at support? So if it is simply supported, this is simply supported beam. If you have uniformly distributed load, its shear is going to be like this. Forget about this line, and should be a straight line, okay? And its bending should be like this. Where do you think this is V and this is M? Maximum bending moment is happening in the middle. Zero shear is happening at the center. Maximum shear is happening at the supports. So into this portion. I mean, normally, if you talk about practicality, then normally you would have L/4 span and L/4 span from the supports. You will have closer spacing of stirrups because shear force is higher. And in the middle portion, which is middle half, the spacing is larger. The reason is that you have less shear force in the middle. That's the reason we have larger spacing. And again, in this picture, you can see that a fixer is fixing these shear links to the main reinforcement. And again, we use this truss analogy to design shear links. And in next slide, I will simply elaborate more on that. The one which you see these angles, this is the angle of a compression strut. And the vertical things that you see here, these are vertical ties or reinforcement themselves.
Joel, just so you know, you said like shear is represented like by the V.
Yeah.
I remember when we was doing like deflection because of due to bending or something, that was also a V. So is there any sort of like difference? Like, can you use the same symbols to represent different things, or?
Yes, capital V always denotes shear force. And when we were doing deflections, I think you would have seen in the structure analysis, you would have seen small v
Oh, okay.
for
Yeah.
deflections. All right. So, for example, for design load, sometimes we use this omega. All right. But if we talk about structural dynamics, we use omega as angular frequency as well. Okay. So two symbols can be similar, but we denote deflection with delta as well.
Okay.
Okay.
All right. Cheers.
These are Eurocode terms as well for shear and moment, but I think that these are very common terms. The only different Eurocode term is that for forces or axial forces, Eurocode uses N. So previously, it used to be F or something, but Eurocode uses N. Thanks for the question. Now, Eurocode 2 uses the variable strut inclination method. In these models, the truss analogy is used, where concrete acts as diagonal strut and stirrups, they act as vertical ties. Concrete is taken as strut and stirrups, they are vertical ties. So dotted line that you see here, these are concrete struts, and the stirrups that you see here, these are vertical ties. And then these stirrups can be inclined to 90 degrees to the compression struts as well, but this is not the normal kind of situation. Normally we use these as vertical so that they cross the path of this concrete compression strut. So this is the dotted line. Compression strut means that the dotted line is the line of cracking. To reduce those shear cracks, we use these vertical ties, and these vertical ties are known as stirrups as well. And when we use these ties, they prevent cracking. As you know that when we use steel reinforcement, it plays a major role in terms of limiting the cracking. And then again at the bottom you can see we have tension reinforcement. And the model that we use is this kind of model for compression strut. And Z is the lever arm. Then here you can see that this is how a beam is going to crack if you apply loading. Now here 2-point loads are applied, and then you can see how this cracking is developing. But I would like to show you a video as well to give you overview of why shear reinforcement is important. When shear cracks appear, the beams or members without shear reinforcement will fail suddenly, and this kind of failure should be avoided at all costs. You saw that the failure was really sudden. To avoid this kind of failure, and you can see that in the middle portion there wasn't much failure, and these kind of cracks, these are diagonal. So these are forming the compression strut. And to avoid these kind of cracks, we use stirrups or shear reinforcement. And the shear reinforcement or stirrups, they are concentrated quite a lot at quarter portion from the support. And the middle half, we can have larger spacing of stirrups because in the middle portion, shear force is not much. Unless if you have a point load resting on a beam. In that case, you will have a lot of shear force at that point. Now, it behaves like a truss. So we have truss-like behavior, and then the members with shear reinforcement change from beam-like to truss-like behavior. And then what happens? The tension stresses are taken by these stirrups, all right? And the principal compression stresses, they remain in compression trusses. And remember that the members should always fail in flexure or in bending rather than shear. In flexure, what happens? You will have a lot of deformations before failure happens. And this gives us sufficient warning to take measures, and ductile failure is always good for safety and it always gives you more time to react. On the other hand, the brittle failure or sudden failure should be avoided in structures at all costs. Now, design terms. Now, for verification of shear resistance, these terms should be defined. First is VRD. RD means design resistance. So VRDC means that the design shear resistance of the member without shear reinforcement. And VRDS is the design value of shear force that can be sustained by the yielding of shear reinforcement. All right. So this is shear force sustained by shear reinforcement. And VRD max is the design value of maximum shear force that can be sustained by the member. This is limited by crushing of the compression struts. Now the design check involves that VED, which is applied shear, that is less than or equal to VRD. That is your design shear, where VED can be obtained by simply having this shear force diagram V, where you can get the maximum value. I mean, ideally, we should find shear force at least the depth of the section away from the support so that you have shear force at this point. But for simplicity, we say that, okay, we will find shear force at the center of the support. Now, what is the procedure? Now, members requiring no shear reinforcement, first of all, determine VED, that is design shear resistance, that will come from shear force diagram, and then determine the design values of shear resistance, VRDC. VRDC is the design shear resistance without stirrup. This is the formula for VRDC. And what are these terms? CRDC, K something. So these terms will be on next slide. And with the minimum of VRDC, this is the minimum value. Then you have to see that if VED, if applied, is less than VRDC, then shear reinforcement is not required. And you have to use the minimum area of shear reinforcement in beams. And the formula for minimum area is ASW min is rho S into BW, where rho is the steel reinforcement ratio, and then S is the spacing between stirrups, and BW is the width of the beam. And then again, I will define these terms in a minute. So for different FCK, you have different rho min. And if this condition is not satisfied, then shear reinforcement is required. For the first case, when no design shear reinforcement is required, then in that case, the design value of shear resistance is given by this formula with the minimum of this formula. Now, what does it mean by K? Again, K is a factor which is equal to 1 plus under root 200 over D, and this should be less than 2. So from here, you find out this factor K. And CRD, again, CRD is equal to 0.18 divided by gamma C, where gamma C is, I think, 1.5. And in that way, you have this second factor as well. Now, rho 1 is again the reinforcement ratio. Reinforcement ratio is always, this is AS1. Now, AS1 is area of tension reinforcement, means that bottom bars. And BW is the width of the beam, D is the depth of the beam. Now this should be less than or equal to 0.02. If it is not, then use this 0.2. 0.02 is the maximum value. And V min is equal to 0.035 K 3 over 2. K was determined little earlier here. And FCK is the compressive strength of concrete. And sigma CP in here, this is related to axial load. If axial load is applied, so NED divided by AC, where AC is area of concrete. This is concrete compressive stress at the centroidal axis. NED is applied axial load and AC is area of concrete. But most of the time in beams, we say that this is 0, unless if you have kind of inclined members. And AS1 is the area of tensile reinforcement. When we designed beams, singly beams earlier, you have this bottom reinforcement. This bottom reinforcement area of that reinforcement is AS1. BW is the width of the cross section in the tension area, so the bottom width, if the width of the beam is different for top and bottom, but in our case, it's going to be same. NED is the axial force, as I mentioned earlier, and AC is the cross sectional area of concrete in millimeter square. Now that was the case when no design shear reinforcement is required. In second case, when members they require design shear reinforcement, in that case you have to use these two formula. Members with vertical shear reinforcement, the shear resistance VRD should be smaller of these two values. Now one is related with ties and other is related with struts. Strut means it's compression strut, ties means these are stirrups. Now ASW is the cross-sectional area of shear reinforcement. S is the spacing of stirrups. Z is the lever arm, which is equal to 0.9D, I think. And FYD is the design yield strength, which is yield FYK divided by its gamma factor. And sigma 1 is the strength reduction factor for concrete cracked in shear. Alpha CW is the coefficient taken into account effects of stress in compression cord. So we will define these terms little later, and then you will know that what these terms are about. So if the reinforcement is required, you have to find these two values, and VRD should be smaller of these two values. Now this theta, you will ask, what does it mean by this theta? Where do we get this? Now if you have a look at this diagram, we have longitudinal reinforcement in tension, which is the bottom one. We have compression reinforcement, which is here. And then we have this dotted line. Now, dotted line represents concrete strut in compression. And this is very useful diagram. So we can see that the concrete strut is in compression. To avoid this kind of crushing or in compression, we have to provide these reinforcement. Now the formula which controls, I think, the compression is this bit, VRD max, and the formula which controls the ties, VR, is VRDS. That is for ties. Now the important thing here is this angle. So this angle can be assumed any angle between 21.8 to 45. Now Eurocode allows this equation to be anywhere between 21.8 and 45. Previously in British codes it was just 45. So if we take the minimum one, then it gives us more economy. So again, I would say that EC2 uses strut inclination. I already determined it's complex than BS 8110, so don't worry about 8110. We're not talking about it. The shear, it uses the truss analogies, certainly. So concrete acts as diagonal struts, and stirrups, they act as vertical ties, as I mentioned earlier. And then we have tension and compression reinforcement. There's only one difference, as I mentioned before, that the British codes, they have fixed value of this theta, which is 45. But in Eurocode 2, it can vary between 21.8 and 45. I was trying to solve this problem and the angle taken was 21.8, and then suddenly you will say that, okay, where did you get this angle from? So that's the reason I thought that I should add something that describes this angle. And then how do we get these angles? It is through so many experiments that are carried out on these beams, and then after that these angles are established. In Eurocode 2, the angle can vary between 21.8 to 45. it can reduce the reinforcement. It can reduce the volume of reinforcement, which means that it is going to be more economical. So you can use any angles, but normally we use the smallest one, which results in greater economy. Now, again, this is truss analogy. I mentioned this earlier. We have these compression struts. In this graph on your right, you can see that this is ASFYD over AS means area of steel and shear, FYD is yield of steel, and divided by S is spacing of steel. Now, the first dotted line that you see here, you can see that the value of area is less, and cot theta is equal to 2.5, means if you take cot 21.8, then you will get this 2.5. The best way would be to get tangent 21.9 degrees and then simply inverse it. So your answer is 2.49, which means 2.5. And these are the test results. This dotted line is the best fit, but the test results are this. So these are the test results. We map these angles around these test results, and then we come up with the solution. And the bottom dotted line is the minimum links. And here horizontal represents the shear strength. So it means that by using smaller angle, you can obtain the same shear strength. So for example, if I draw a line here, so you can obtain same shear strength but with smaller area with Eurocode. And if you use cot theta equal to 1, which means that theta is equal to 45, then you can see that you have to have larger reinforcement. Click here to watch worked example on shear design of reinforced concrete beams as per Eurocode 2. Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.